Moving on, let's now discuss coupling, positioning, and triggering. Coupling is a means of displaying the waveform with or without any DC offset and grounding it. As such, coupling takes three forms: DC coupling, AC coupling, and grounding. When viewing a waveform with DC coupling, the oscilloscope includes any DC offset. When viewing a waveform with AC coupling, the oscilloscope removes any DC offset and assumes the incoming waveform is entirely AC, zero-centered. Ground coupling flatlines the display. For an application of this feature, let's start by displaying our test waveform using a vertical sensitivity of 2 volts per division and a horizontal sensitivity of 500 microseconds per division. As can be expected, our 5-volt pulses are entirely on one side of the axis, have a magnitude of 5 volts, being 2.5 divisions at 2 volts per division, and they've got a period of 1 millisecond, being 2 horizontal divisions at 500 microseconds per division. To access the coupling menu for a specific channel, go to the menu of the channel of interest by pressing the menu button immediately above the scaling knob. This is yet another button you have been granted specific authorization to press. This opens the channel menu on the screen. By the way, it's not a touch screen, so keep your greasy fingers off of it. Everybody thinks everything's a touch screen nowadays. The selection buttons on the right-hand side of the screen allow a user to choose from the available options. Press the button next to coupling. As can be expected, we're currently in DC coupling mode since the waveform includes a DC offset and the oscilloscope is displaying this waveform entirely on one side of the axis. If we rotate the multipurpose knob inside the operation and functions group to AC coupling, and then press the multipurpose knob to select it, note really nothing has changed about our waveform, only the oscilloscope has removed the DC offset and zero-centered it, assuming everything is AC. This is where it's helpful to think of our test waveform as not as alternating pulses of 5 volts and 0 volts, but rather an AC waveform that alternates between positive 2.5 and negative 2.5 volts that includes a 2.5 volt DC offset such that it's shifted entirely to one side of the axis. Note, AC coupling is a principal source of trouble for individuals viewing DC waveforms. If AC coupling removes all the DC, when displaying an entirely DC waveform, flatline output is to be entirely expected. DC coupling shows the waveform in its unadulterated form with both DC and AC components. AC coupling drops the DC and can sometimes give a user a false impression if they aren't aware of this modification. If we rotate the multipurpose knob inside the operation and functions group to ground coupling, and then press the multifunction knob to select it, note the oscilloscope flatlines at ground. This setting is helpful if you're totally lost and just need to figure out where the trace is. By the way, you can turn off a channel entirely by pressing the menu button more than once. Press the menu button again and it'll return. While we're ground coupled, let's examine positioning. The third button at the top of each channel in the vertical group is the positioning knob that can be used to vertically reposition a waveform on the screen. This is especially helpful when comparing 2 or more waveforms on the same screen. If we rotate the position knob for channel 1 so that the trace is in the bottom half of the screen, and then return to DC coupling, note that the waveform has simply been repositioned such that the waveform is in the bottom half of the screen. Again, the test waveform is still 5 volt pulses at 1 kHz, only the horizontal axis has changed as indicated by the yellow channel 1 marker on the left-hand side. Positioning is yet another source of trouble for individuals new to oscilloscope, especially when a trace has been positioned excessively high or low. This displacement can sometimes confuse a user if they aren't aware of this modification. One can always return the trace to the center and reposition as needed. Let's now talk about triggering. Triggering, to use a rather apt analogy, is the means the oscilloscope uses to figure out where the 1 beat is in a particular musical composition. If you tell the oscilloscope to wait to gather data until the periodic waveform under inspection is rising and reaches, let's say, positive 1.2 volts, and do so on a regular basis for a specific sample window, the oscilloscope will sit there until it experiences this triggering event and dutifully sample the waveform for the required amount of time on a regular basis. As long as the triggering event regularly occurs, the oscilloscope regularly samples the waveform and spits out data. For our sample test waveform triggering at 1.2 volts going positive would mean the oscilloscope establishes roughly the first quarter rising edge of our pulse as our 1 beat. Every time the score hits the 1 beat, the oscilloscope captures the window of data and displays it on the screen. Given our waveform is periodic or repetitive in nature, establishing a particular 1 beat isn't all that important. For example, if we triggered not at 1.2 volts going positive, but rather 2.48 volts going positive, this just means the oscilloscope uses 2.48 volts and rising as our 1 beat. To adjust the trigger level, one uses the triggering knob. When adjusting the triggering level, you'll see the level rise or fall. As previously, every time the score hits the 1 beat, in this case 2.48 volts, the oscilloscope captures a window of data and displays it on the screen. Really nothing has changed, only the repetitive waveform is being sampled at a different moment, thus shifting our capture window ever so slightly. Display problems arise when a user attempts to establish a triggering condition that the waveform never achieves. For our sample test waveform, triggering at, let's say, 6 volts going positive would mean the oscilloscope never establishes a 1 beat, since the waveform under inspection tops out at 5 volts. Given this unattainable condition, the oscilloscope loses the beat and the display starts this annoying drift. The drift is hard to capture on a still picture, but a video clip shows the jitter a little better. This annoying effect is amplified when viewing faster signals using a larger time span on the horizontal axis. Long story short, triggering off nonsense conditions yields astable results. Triggering also implies that the waveform under inspection must be periodic or regular and repetitive in nature. For introductory circuit analysis, this is most often the case. However, digital waveforms, packets of information transmitted by irregular pulses of voltage, isn't repetitive, and triggering off non-repetitive waveforms can be tricky. For this reason, the oscilloscope includes the ability to momentarily capture a specific window on a one-time basis. The run stop button in the upper right allows this ability. In green run mode, the oscilloscope is constantly sampling and refreshing the screen, whereas in red stop mode, it samples the waveform once, scribbles it on the screen, and sits back there ready to fetch. Long story short, an oscilloscope needs to trigger off an event that actually occurs on a regular basis. If I waited to start lab until your lazy lab partner showed up on time and prepared, we'd never get anything done because it's never going to happen. Similar to the means of positioning a channel vertically, the triggering event can also be repositioned horizontally using the horizontal position knob in the horizontal group. By turning this knob clockwise or counterclockwise, a user can shift the waveform under inspection horizontally left or right. Consider these three displays of the same waveform triggered at 1.2 volts and rising, horizontally repositioned. They're all the same waveform, only shifted left or right, as indicated by the orange trigger marker on the top. Alright, this about wraps up our brief introduction to the oscilloscope. Since we introduced a lot of different important concepts in a short time span, let's do a quick review and discuss common oscilloscope troubleshooting events before we say goodbye. The screen displays voltage on the vertical y-axis and time on the horizontal x-axis. The screen also displays menu-specific items, and items within a menu can be selected using the buttons on the side of the screen, as well as the multi-purpose knob in the operations group. The vertical group includes 2 channels. Each channel has a means of scaling the volts per division, a means of accessing that channel's menu, and a means of vertically repositioning that channel on the display. The horizontal group includes a means of scaling the x-axis seconds per division and a means of horizontally repositioning that channel on the display. The triggering group includes a trigger menu and a means of adjusting the triggering event up or down. Triggering must occur off an event that actually occurs on a regular basis. DC coupling includes the DC and AC aspects of a waveform under inspection, whereas AC coupling removes the DC component and assumes everything is zero-centered. Ground coupling flatlines the trace. Attenuation is the means of reducing a signal. A probe often includes a slider that attenuates or does not attenuate the signal depending upon the position. A modern oscilloscope can compensate for probe attenuated input using the channel menu to rescale the signal. As brief as this list seems to be, I will be so bold to say that every broken oscilloscope I've seen, by the way I'm using quotation marks with my fingers, isn't broken, but rather one or more of these basic aspects aren't being taken into account. Let's examine each aspect in turn. For the vertical group, if the oscilloscope is improperly vertically scaled, your waveform will look comically small or so gargantuan it won't fit on the screen. Here's our test waveform with 5-volt pulses at 1 kHz, visualized at a vertical sensitivity of 5 millivolts per division, 2 volts per division, and again at 5 volts per division. all have the same horizontal scale at 500 microseconds per division. Don't get me wrong, all these levels of magnification do have their uses. It really depends if a user is interested in a quick snapshot, a whole pulse, or if their concern is minute levels of electrical noise. If the trace is vertically positioned excessively high or low, you might not be able to find it. Here's our test waveform using a vertical sensitivity of 2 volts per division and a horizontal sensitivity of 500 microseconds per division, at the bottom of the screen, in the center, and at the top. For the horizontal group, if the oscilloscope is improperly horizontally scaled, your waveform will look super spread out or jammed too tight. Here's our test waveform visualized at a horizontal sensitivity of 50 milliseconds per division, 500 microseconds per division, and again at 1 microsecond per division. Additionally, be aware that waveforms with excessively slow frequencies aren't well suited for display on an oscilloscope. In regards to triggering, triggering must occur off an event that actually occurs on a regular basis. If you're triggering off an event that never occurs, or does so on an infrequent basis, the oscilloscope just picks a beat and plays a tune that may not be the song you want. An oscilloscope triggering properly inside the range of the waveform under inspection will hold still and let you get a good look at it. Additionally, make sure the oscilloscope is triggering off the channel you want. The default setup for most oscilloscopes triggers off channel 1. However, this isn't always the case. The triggering menu above the trigger level knob allows a user to select a triggering source, channel 1, channel 2, or some other external source. If you're triggering off channel 2 and there's nothing on channel 2, the oscilloscope loses the beat. Trigger off sources and events that actually exist. In regards to coupling, DC coupling includes both the DC and AC aspects of the waveform. AC coupling, in contrast, removes the DC component and assumes the waveform is zero-centered. If you're trying to measure pure DC while in AC coupling mode, you are using this feature wrong. Here's the test waveform visualized with DC coupling, AC coupling, and a ground. In regards to attenuation, if you're seeing values 1/10 of what you expect, you are inadvertently attenuating the waveform. Check the slider and make sure it's in the position you want. Additionally, it should be noted that modern oscilloscopes allow a means of dealing with attenuated input by rescaling it to the original value. If you're using 1x attenuation and the oscilloscope is set up to rescale 10x attenuated input, the results will be 10 times what you expect. Long story short, both the probes and the oscilloscope need to be in the same attenuation mode. The attenuation level for a channel is to be found in that particular channel's menu on the Tektronix TBS 1032B digital oscilloscope. Here's 4 plots of the test waveform with different levels of probe and oscilloscope attenuated inputs. The first plot is when the probe is set up for 1x attenuation and the oscilloscope is expecting 1x attenuated input. As we'd expect, everything is as it should be. The second plot is when the probe is set up for 10x attenuation and the oscilloscope is expecting 1x attenuated input. The magnitude is 1/10 of what we'd expect. The third plot is when the probe is set up for 1x attenuation and the oscilloscope is expecting 10x attenuated input. The magnitude is 10 times of what we'd expect. Finally, the fourth plot is when the probe is set up for 10x attenuation and the oscilloscope is expecting 10x attenuated input. Given there's an established conversion factor, everything is as it should be, although the display does show some artifacts at the corners. Finally, given all the user-adjustable features in an oscilloscope, often the source of errors is not the current user, but rather the previous one. If the previous user happened to set up the oscilloscope with an odd vertical and horizontal sensitivity, position the trace bizarrely, use some abnormal triggering condition, attenuated it weirdly, or perform some other advanced option like inversion or mathematical function, that oscilloscope will appear to act weird, odd, strange, abnormal, bizarre, unusual, and peculiar because, and this is important, it's being told to act weird, odd, strange, abnormal, bizarre, unusual, and peculiar. Your job is to be capable of setting the oscilloscope up so it snaps out of it and flies straight. This is often a task of simply walking through this list and figuring out which aspect, vertical, horizontal, positioning, triggering, coupling, or attenuation of the waveform under inspection is distorted and rectifying it. Hopelessly tangled scenarios can also be remedied by restoring an oscilloscope to the default or some pre-established standard setup. And maybe lab standard operating procedures to begin and end each lab with a given condition. Importantly, all use of all instrumentation, including the oscilloscope, in all scenarios must always be preceded by one event. That event being, do the calculations first. You need to know everything you can about the waveform under inspection in advance. Set up the instrumentation to respond to these conditions and be smart enough to recognize when something is amiss. Case in point. I know the test waveform has 5-volt pulses entirely on one side of the axis, operating at a frequency of 1 kHz. Prior to hooking up the probe on channel 1, I set my oscilloscope up as follows. I'll use a vertical sensitivity of 2 volts per division. With 5-volt peaks, I know the test waveform will be roughly 2.5 divisions tall. I'll vertically position the trace in the center of the screen. I'll use a horizontal sensitivity of 500 microseconds per division. With a 1 millisecond period, I know each cycle of the test waveform will take 2 full divisions. With a 50% duty cycle, one 500 microsecond division will be on, and one 500 microsecond division will be off. I'll trigger off channel 1 at 1.2 volts and rising. This is a regular event in the test waveform's life. I'll use DC coupling. The waveform includes a DC offset, and I want to see this DC offset. The probe is set up with 1x attenuation, and the oscilloscope is expecting 1x attenuated input. When I hook up the channel 1 probe to the test point, I am rewarded with a stunning snapshot of the waveform under inspection. It's not distorted, deformed, or dorked up, and importantly, I didn't waste my time. To quote one of the smartest, funniest, and most handsome dudes on the internet, imagine how well lab will go if you know what you're doing. If in sheer desperation you don't know what you're doing, modern oscilloscopes offer the frustrated user a lifeline in the form of an auto set button, use of which is tacit admission of your ineptitude. The auto set button turns overscaling to the oscilloscope, which may or may not offer the level of detail you seek. As an example of this, when I press the auto set button, notice the oscilloscope uses my earlier vertical and horizontal sensitivities of 2 volts per division and 500 microseconds per division, only changing the triggering level ever so slightly. Additionally, you'll notice a host of measurement options magically appear on the oscilloscope screen, among them peak to peak, period, and frequency. This is to suggest that much more oscilloscope fun awaits. We'll examine manual and automated means of measurement using the oscilloscope and more in later lectures. Until then, that's about it for this quick introduction to the oscilloscope. We'll be making use of this tool in later lectures to display and measure the electrical characteristics of elements within AC circuits. In conclusion, this lecture took a brief look at the oscilloscope, a device that not only measures the voltage waveform under inspection, but also displays a plot of it on the screen. We oriented ourselves to the device and learned how to properly vertically and horizontally scale, position, trigger, couple, and attenuate a voltage signal for display and measurement purposes. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you properly scale your oscilloscope in advance. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.